All right, so far we've been talking about power and power triangle, complex power within AC circuits. And so now let's actually solve one. The first thing that I like to do on all of these problems is to label my components with the impedances. They're already giving us reactance in 10 ohms and in 20 ohms. But in order to turn that reactance into impedance, my inductors need positive J's and my capacitors need negative J's. Another thing you can do with every circuit in this whole class is to label nodes. Here's some nodes here. If you wanted to put it A, B, C, call this my reference, and we'll call it G, A, B, C, and G. There's my nodes. And what we're asked to find is the total power. So we have the total voltage as 120 volts, angle 0. In order to find the total power, we're going to use S equals VI complex conjugate. All of those are vectors. Well, in order to get that, how do I get I? Well, I can use our favorite law, Ohm's law. V equals IZ. All of these being total. I have my V total. My I total is what's going to come out of this source. That'll plug into here. All the totals. Z total. How do I get Z total? You just add all of these up according to their relationships. So the first thing I can see is that this J15 is in series with 30. Series means they exclusively share one node between them. They exclusively share C. One node coming in, one node coming out. Another way to think about it is the same current that flows through here keeps flowing through there. These are in series. The next one is parallel from B to G. Negative J20 shares the same two nodes as these two together. If we're using the box method, these are in a box. And so together, they should have B and G on the outside, which is the same as negative J20 has B and G on the outside. It's in parallel. Put all of this in a box, and it exclusively has B between it plus J10. Put brackets around that because all of this is what's in series with the J10. So now I have Z total. The way that would look on a calculator, 1 over J15 plus 30 plus 1 over negative J20. All of that gets added to J10. And if we plug all of those together, Z being a vector here, because we're inside of AC, Z being a vector gives me 15.16 angle negative 31.14 ohms. I could go from polar to rectangular. If I prefer the answer in rectangular, 12.98 minus J 7.84. And the way that this would look in a circuit, if you cared to understand it this way, every circuit has a source, a path to the load, path back to the source, right? And then together, that would be 12.98 minus J 7.84. So what this tells me, this negative J tells me that it is a capacitive circuit. It tells me that the resistance, the total resistance is 12.98 and the total reactance is 7.84, and it is a capacitive circuit. 120 angle 0. That's what we've just formed. And so now we have the total. So the delivered to this load is the same as the delivered by the source is the total. And you just plug, oh, one more step. Got to plug in V equals IZ, I equals V over Z, I equals V over Z, 120 angle 0, 12.98 minus J 7.84. You could also plug it in as the polar. Your calculator doesn't care, and neither do I when it comes to Z, because it means something. Rectangular of Z means something. So I plug that in my I total, which is the same as saying I coming out of the source right there. The I source in this case is 7.92 amps. Angle positive 31.14 degrees. So now I can plug those in together. S equals VI complex conjugate. Complex conjugate means that this angle is just reflected on the real axis. So if my angle is positive 31.14, the conjugate is negative 31.14. This being the j-axis, this being the real axis. So if this is my angle, then this is the complex conjugate. So S total, S being complex power, this is a vector, so we see it's complex, 120 angle 0 times I, 7.92 angle negative 31.14. My S total comes out to 950.4 angle negative 31.14 degrees. That is complex power. This is in the polar form, and I can go straight to the rectangular form, and then I will have all four components of my power triangle. When I go from polar to rectangular, I get 813.45 minus J 491.48. This right here is the real power. This right here is the reactive power, Q. If I'm forming a triangle, this P is the real axis. This is a negative Q. This is also a negative angle. Here's about 30. There is my Q. Q, 491.48 volt amps reactive, 491. P, 813.45 watts. Real power, watts, just like it was in DC. Right there is the magnitude of S. I'm looking at a vector. Scoot that puppy up. The magnitude of the vector is the apparent power when it comes to complex power. Apparent power. Its value is 950.4 volt amps. And right there is theta T. Theta T is equal to negative 31.14. If I was asked for the power factor, I could either take cosine of theta T or I could take P over S. And either way, I'd get the same answer of 0.856. And this is a leading power factor because it is a capacitive circuit. It tells us the relationship between I to E. So if you need to remember I, when it leads E spells ice, C is capacitive. The other way you could do it is just memorize. If you have a negative theta angle, you have a leading power factor. And with that, we have our final answer right here. If you have any questions, you should reach out to your instructor. Thank you.